Okay, in this example, we are asked what are the real cube roots of 125. As far as what this means, it's really referring to what possible numbers can we raise to the third power to get 125. Well, the only possible number we can do that with is 5. 5 to the third is 125. So, 5 is the only cube root of 125. Or at least real cube root. And for this, we're essentially cube rooting both sides. So that if we have x2 an odd exponent equal to a number, then x will be equal to the nth root of that number. Again, that's only if it's odd. If it's an even exponent, then it applies a little bit differently for all real roots. In this example, we're asked what are the real fourth roots of 16. So that is asking us what numbers to the fourth power will give us 16. In fact, there's two possibilities for this. There is both positive 2, because 2 to the fourth is 16, and negative 2 to the fourth is also 16. So there's actually two possibilities. You may recall a property from earlier that said if we have something squared equal to a number, then x is equal to plus or minus the square root of that number. Well, this applies to all even exponents if we extend it further. If we have x to the power of n, where n is even, then x will equal plus or minus the nth root, again when n is even, of a. So the two possible fourth roots are both positive 2 and negative 2. So in this little vocab, we're just interpreting fractional exponents. In other words, rational exponents. So when we interpret rational exponents, it's essentially just having the top number being a normal exponent and the bottom number being an index. So if we have 4 to the 3 over 2, this top number is an exponent, bottom number is an index or a root. And you can write it in one of two forms. You can write it as 4 squared, or 4 to the third, the square root of 4 to the third. Or you can write it as the square root of 4 all raised to the third. And while we're looking at this, remember that the square root is the index that's implied. So we can write it as the square root of 4 to the third as well, or the square root of 4 to the third. So remember, with the index of 2, you don't actually have to write it. Okay. In this example, we're evaluating the expression 16 to the 1/4. Now, in order to do this, it helps to interpret what the fractional exponent means as a radical. A fractional exponent is just a way of writing a combination of an exponent and an index, or a root. So if I change this into one of the radical forms, I can rewrite it as the fourth root of 16 to the first, or you can write it as the fourth root of 16 being raised to the first. So you can either have the exponent on the 16 itself or on the whole expression outside the radical. It's the same thing. But either way, it is still interpreted as the fourth root of 16. Usually it's easier to deal with the radical when you're first when you're trying to evaluate, and then deal with the exponent afterwards. Usually, not always the case. But the fourth root of 16 is 2, because 2 to the fourth is 16. And since the exponent is 1, 2 to the first is just 2. Okay, in this example, we're going to interpret the fractional exponent in terms of a radical. So remember, the bottom number is a root, or the index with the radical, and the top number is an exponent. When you're usually doing this, it is usually better to use the parenthesis version with the exponent on the outside and the root on the inside. Well, now that we have it rewritten in terms of a radical, just start by breaking down the inside. The fifth root of 32 is actually 2. 2 to the power of 5 is 32. So that becomes, breaks down into 2 to the power of 3 now. And then 2 to the power of 3 is 8. So overall, 8. Okay, once again, we're going to be evaluating an expression. We have 27 to the negative 2/3 power. As I go to evaluate this one has a negative exponent, so it's a little bit different. So I'm going to start by dealing with the negative exponent. Negative exponents just means to switch it to the reciprocal or move it into the opposite part of the fraction. So since it's 27 as a whole number, we will move it down to the bottom of a fraction, making it 1 over 27. This will allow us to make our exponent a positive number now, so 2 over 3. Once we do this, we can now just go through the same process, turning the exponent into a radical form. So 1 over the top number is the exponent, so 2 is the exponent, and the index is 3, so it's the cube root of 27. So remember, exponent over index. Now that we have this, the cube root of 27 is 3. And then we have the exponent still on the outside. So 3 squared is 9. So overall, we have 1 over 9. Okay, in this example, we're going to be looking at the fifth root of 32m to the 15th. Now, when it comes to simplifying radicals, remember that if it's connected by multiplication, like the 32 and the m to the 15th are, we can separate it into two separate radicals, as the fifth root of 32 times the fifth root of m to the 15th. It's a property we've used earlier in Algebra 2 to break down radicals when dealing with the quadratic formula and simplifying complex numbers when we have negative numbers underneath square roots. Now that we've separated the fifth root of 32, 32 is a perfect fifth power. It is just 2. For the variable, I'm going to look at it as a fractional exponent real quick. Remember, it's exponent over index. So it would be written as m to the 15th over 5. And 15 divided by 5 is a whole number, so that is awesome. We don't have to break it apart anymore. So it would just be m to the 3rd. And this is the simplified version. Okay, in this example, we are simplifying an expression, the fourth root of x to the 20 and y to the 8th. As we go through and do this, because the two variables are connected by multiplication, we will separate them into two separate radicals. So the fourth root of x to the 20th times the fourth root of y to the 8th. Now that we have this, if I examine it as a fractional exponent, it would be x to the 20 over 4, which would be a whole number. 20 over 4 is 5. So it simplifies into be x to the 5th. And on the other hand, for the y to the 4th, the fourth root of y to the 8th, well, as we look at it as a fractional exponent, exponent over index, 8 divided by 4 is 2, so it simplifies to be y squared. Now, this actually has a little bit of a problem here. This is an even root. Even roots and variables kind of cause issues. There's certain numbers that these variables can't be. For instance, we can't take the root of a negative number for an even root, that is. So like the square root of negative 4 doesn't actually exist. And right now we are not going to be dealing with imaginary numbers because we're really just introducing higher power roots. And the fourth root is not the same thing as the square root. So you wouldn't just put I. It gets a little bit more complicated than that. So we have to eliminate the possibilities of our variables being negative. And the way we simply do that is after simplifying the radicals, we just put absolute value bars around the variables. So we would put absolute value of x to the fifth. You can also put it as the absolute value of x to the fifth like that. Either way, we get the same result. You would do that for each variable under certain conditions. So you'll notice that I haven't put it around the y and instead only put it around the x. And that's simply because my y, after being simplified, has an even exponent. And when you raise a variable or a number to an even exponent, it will always be positive. So this eliminates the possibility of the negatives without having to add the absolute value bars. So, in short term, the absolute value bars would be needed when we have an even root, but the result of being simplified is an odd exponent. However, a lot of times in classes you will see an exclusion saying like x is greater than 0 and y is greater than 0. So in those cases, you wouldn't need the absolute value bars and you would just write it as x to the fifth y squared. Since we don't have that here, we should be including the answer with the absolute value bars. So we're going to solve this simple equation. One of the most basic strategies for solving equations is with reverse order of operations. So please excuse my dear Aunt Sally. We would start by getting rid of addition and subtraction, but in this case there is no addition and subtraction. So next we would get rid of multiplication and division. We are multiplying by 2, so to get rid of it, we'll divide both sides by 2, giving us x to the fifth is equal to 32. Now after doing that, we still have to get rid of the exponent. Oftentimes you'll see it as us taking the fifth root of both sides. You'll hear it often referred to that. Fifth root and fifth power are opposites and would then cancel out, leaving us with x is equal to, well, the fifth root of 32 is just 2. So in this example, we're solving an equation. So just start by doing reverse order of operations. We only see the variable one time in this equation. So reverse order of operations should get the variable by itself. So there's no addition and subtraction. So we'll start by dividing both sides by 2, giving us p to the fourth is equal to 81. Now, a lot of times you'll see it as doing the fourth root on both sides. That's not quite what's happening here, but you will often see it. Essentially, if you have p to an even power equal to a number, where this is even, then p is equal to plus or minus the nth root, or that even root of the number. So if we look at it, we'll have p equal to plus or minus, because it's an even root. The even roots, when you're finding solutions, will have both positive and negative possibilities. So the plus or minus the fourth root of 81. And the fourth root of 81 is 3. So p is plus or minus 3. Or as another way of writing it, 3 and negative 3. So in this example, we have one cube-shaped container which has an edge length of 2 centimeters longer than the edge length of a second cube. The volume of the larger cube is 729 cubic centimeters. That should be cubic right there. When the largest cube empties into the smaller cube, how much water will spill? So the amount of water that would spill would equate to the difference between the two. So we'll have to find the amount of water in the larger and the amount of water in the smaller, and then subtract the two. That's the idea behind this. Once we find that, we'll get the amount spilled. We do know the amount in the larger is 729 cubic centimeters. We don't know the amount in the smaller. However, we do know that one of them has an edge length of 2 centimeters longer than the other one. The one with the edge length of 2 centimeters longer would be the large cube. So we can say that whatever the short cube side is, plus 2 to the third would equal 729. Now this is a simple equation which will allow us to solve for x, and x would represent the side of this shorter cube. So going through solving it, because the 2 would be added before cubing it, we would have to get rid of the stuff outside the parentheses first. So we would have to get rid of the cubing first. And we'll do that by cube rooting both sides, giving us x plus 2 equals 9. And then if I finish solving, we'll subtract 2 from both sides, giving us x equals 7. So the side of the smaller cube would be 7 centimeters. Now this is just the side length, not the actual volume, not the amount of water contained in the cube. Well, the formula for volume of a cube is just the side length to the third. So the smaller one will have a volume that is 7 centimeters cubed. In other words, 343 cubic centimeters. So back to the problem at hand, we have the larger volume at 729 cubic centimeters, and we have the smaller one at 343 cubic centimeters. Just subtract the two and we get the amount spilled, which is 386 cubic centimeters of water spilled.